In this series, I have been talking about having an expectation of the probability that a randomly sampled unit will be placed into a specific category. In this video, we're going to look at a goodness of fit statistic, which is a way of comparing what we observe to what we expect. Here is an example of a multinomial distribution. We have 4 observations, and the probability of drawing an observation from the population and categorizing that observation in the first category is 0.5, in the second category is 0.25, and in the third category is 0.25. We used the multinomial coefficient, shown here at the bottom, to calculate the probability, and we did so for each of the possible outcomes we could get with 4 observations. This provides our multinomial distribution. Given these parameters, how can we determine which sets of observations are least expected? I know what is the most expected, and that is to have half of these 4 observations end up in category 1, a quarter of the 4 observations, or 1 observation, end up in category 2, and 1 observation end up in category 3. And indeed, when I look at the multinomial distribution, I see that 2 in category A, 1 in B, and 1 in C has the highest probability of any of the possible outcomes. What is less clear to me is when I have 1 observation from A, 0 from B, and 3 from C, whether that is as good of a fit to what I expected here as when I have 1 observation from A, 2 from B, and 1 from C. I recognize that the probabilities are different, and I might be inclined to go with the smaller probability, but my question is about which one of these fit best or worst with my expectation based upon this set of parameters of 0.5, 0.25, and 0.25. Here's the setup for a goodness of fit statistic. Consider a multinomial distribution with 3 categories, each with a known probability that a random observation will be placed into that category. Also suppose that we make 4 observations. This is like the multinomial distribution we were just looking at. Pi 1 is 0.5, pi 2 is 0.25, pi 3 is 0.25, and n equals 4. For any one of our categories, if we know the probability of an observation fitting that category and know how many observations we will make, we can calculate how many of the observations we expect to make in each category. So we expect in category 1 for half of our 4 observations to be in that category, and that's 2. We expect in category 2 for a quarter of our observations to be in that category, and that's 1, and the same for category 3. The fact that we expect that, however, is not necessarily what we will obtain. Remember, we're randomly sampling from a population in which the categories are represented in the proportion that we've defined here, but random sampling means that randomness will be involved, and we could end up, for example, with all 4 in the first category or all 4 in the third category. The question of interest is, how do we assess goodness of fit with what we expected? For any of our categories, if we know the expected and observed values for that category, we can calculate the goodness of fit, or more precisely, the lack of fit, for each category, and we do so with this formula. X squared of fit for the kth category equals our observed number of observations from that category minus what we expected from that category, quantity squared, divided by what we expected from that category. You may wonder, why are we squaring and why are we dividing? If you are familiar with the variance formula, or sums of squares with quantitative variables when we do least squares regression, you know that we take the deviation from the mean and we square because we are interested in the value of the deviation without regard to the sign, and that is the same thing here. It doesn't matter if our observed values are below what we expected or above what we expected. What matters is how far it is from what we expected, so we square to get rid of the sign, and then we standardize by dividing by the expectation for that category. Consider that we are looking at the number of observations we placed in a category and how it differs from what we expected for that category. How big is that difference? It depends. What does it depend on? It depends upon what we expected from that category. If we expected a large number of observations in that category, then in relative terms, a larger deviation is not as big of an influence than if we had expected a small number from that category. The relativeness of that deviation depends upon how many we expect to come from that category. So again, the goodness of fit statistic for any of our categories is the square of the difference between the number of observations in that category and what we expected, and then standardized by what we expected in that category. Here's an example. For category A with n equals 4, when we classify 3 of the 4 in category A, then we would take 3 minus 2, that is our observation minus what we expected, square it, and then standardize it by dividing it by what we expected, which is 2. So the x square of fit for category 1 is 0.5. A goodness of fit statistic for our entire study is simply to sum the goodness of fit across all the categories. So once we have calculated goodness of fit for each category, sum those up, and that is a goodness of fit statistic that will tell us something about how well our sample fits with what we expected. For example, when the placements into category A, B, and C are respectively 3, 1, and 0, using the probabilities of 0.5, 0.25, and 0.25, our goodness of fit statistic equals 0.5, the goodness of fit or lack thereof for the first category, plus 0, the goodness of fit or lack thereof for the second category, plus 1 for the third category, giving us a total goodness of fit statistic of 1.5.